the cloud.
So today we are going to talk about FRW cosmology. So FRW cosmology is a model of the space-time, which was inspired by the way the space-time look like at very large scales, which is that it looks to be homogeneous and isotropic at very large scale. So the FRW model, it consists of a set of preferred observers who all experience the same history, at least at some well, that is the definition of FRW. Now, of course, the universe that we live in is not exactly homogeneous and isotropic. We exist in it. At shorter scales, everything is anisotropic and inhomogeneous. But the idea is at larger scales, it is relatively homogeneous and isotropic. And we want to make an idealized model for that, so which is exactly homogeneous and isotropic. So the idea is that there are these observers so there is a family of preferred observers who experience the same history, and therefore there will be some preferred time slices measured by the clock of these observers. So we imagine they have clocks. They measure time, and at some point they synchronize their times. And then there will be preferred time slices. At constant values of their times. And these slices are maximum, these time slices, which are the space-like hypersurfaces, these are maximally symmetric. Which means that, so all points on these slices, on these 3D hypersurfaces, so these are 3D space-like hypersurfaces, these are, all points on them are identical, and there is no preferred direction. So therefore, the geometry is fully determined by the scalar curvature. Once I know the scalar curvature or the Ricci scalar, then I know everything about this geometry. Okay, then, so with then the full structure of the metric, if I use the time of these observers as a time variable, then the full metric will have a very simple form. Or I should say that, so this scalar curvature can have 3 different values. So it's either, these slices are either positively curved, so either R is larger than 0, R is equal to 0, or R is less than 0. If it is positively curved, we call them closed or spherical, because that's how it's because they are, at least locally, they are equivalent to a 3 sphere. When R is 0, we call them flat, so they are equivalent. Locally, they are the same as the Euclidean space, R3. And then if R is negative, then they are called open or hyperbolic. And then the metric for such a spacetime can be written as some overall scaling. So the size of the size of these, the slices, they can change with time. Therefore, the curvature, by the size, I mean the curvatures can depend on time. But up to this rescaling of the curvature or the size, they look identical. So therefore, the metric can be written as some scale factor that just rescales these surfaces times some fixed metrics, fixed spatial metrics with a fixed curvature that we set to 1 if it is non-zero, to 1, 0, or minus 1. So that's how it looks like. So if K is equal to 1, we recognize this as the metric of a 3-sphere. So this space is nice. If K is equal to 0, then we are Euclidean, and then K equals -1 correspond to hyperbolic. Hyperboloid. So what I did was that I set, so I consider these metrics which have which have curvature lengths equal to 1 in the case of 3-sphere and hyperbola. Of course, I can do that by a redefinition of the scale factor and this R variable. So the physical curvature of these slices will change in time, but that change is just a rescaling that is captured by the scale factor. So this is the form of the metric. And this is it's a very simple metric for which we can even calculate the Einstein tensor and Riemann curvature, Ricci curvature, and Einstein tensor. We can do it even with hand to derive Einstein equations. But before that, let me also talk about the structure of the energy momentum tensor. So we want to consider this model together with some matter field. So at the end of the day, we want to solve the Einstein equation for this model. So there will be, we have a metric, and we want to also talk about the stress energy tensor. So now for the energy momentum tensor, what is the form of the energy momentum tensor under this assumption of homogeneity and isotropy? The form should be of this form. T mu nu should be diagonal, and also all the spatial part have to be the same. So, and I call them rho minus rho. I call T00 minus rho, and then the other the spatial parts, I call them P. Why is this like that? Because T0I is a vector, and therefore it has to be 0 because there is no preferred direction. Also, the spatial pi should be proportional to delta ij, because this is the only tensor which is invariant on the rotation. So if it was anything else, then on the rotations it would change. But we say that it is isotropic, so therefore it shouldn't. It should be proportional to the unit vector. And then the constants of proportionality for T0 for this the spatial part chi p, and then T00 chi minus rho. Of course, this is the way that the stress energy tensor of a perfect fluid looks like. So these names rho and p are given in analogy with the energy density and pressure of a perfect fluid. So the statement is that under the assumption of homogeneity and isotropy, the energy momentum tensor will have the form of energy momentum of the perfect fluid. Even if the matter fields or whatever are providing those that T mu nu is not actually a perfect fluid, under these symmetries they look the same as the perfect fluid. Okay, so now now we can write the Einstein equation. For this space-time. So it's enough to write the 0,0 component of the Einstein equation and energy momentum conservation. The 0th component of energy momentum conservation. So since this model is relatively simple, these two equations will contain all of the information. These are the equations that follow from this. Contain all of the information about this space-time. Or all of the dynamical equations. So from the 0,0 component of the Einstein equation, we get the following equation. We get a dot over a squared is equal to 8 pi g over 3 times rho. So rho comes from T00, and then there will be a component contribution coming from the spatial curvature of the metric that I'll take it to the right hand side of the equation. So that will be k divided by a squared. So remember, k can be 0, plus 1, or minus 1. And then from the conservation of T mu nu, maybe I can derive it here. So we have d mu, del mu, T mu 0 equal to 0, that we can write as 1 over square root of minus g d mu square root of minus g T mu 0 minus 1 over 2 d0 of g alpha beta t alpha beta equal to 0. Now we know that the square root of minus g is a cube for this space-time. Well, the time well, here this is correct only if I am in the k equal to 0 case. So there would be an additional piece if I'm in the k equals +1 or -1, but that wouldn't be time dependent. And since our t mu nu is diagonal, if I have 0 index here, mu has to be 0, so I will get only the time derivative. So I wouldn't care about the time independent part of this. So let me write it like that. The time dependent of a square root of g is a of tq. Because if we remember, this is the form of the metric. So I have 3 components of the metric that have a factor of a squared. So when I take the determinant, the square root of the determinant, it gives me a factor of aq. So this equation becomes 1 over a cubed d0 of a cubed t0, 0, which was minus rho. And then here, the only component of G that has time dependence is the spatial component. So I will get minus 1 over 2 d0 of a squared divided by a squared gij tij equal to 0. So the first term gives me minus rho dot minus 3h rho, and the second term gives me minus 3hp, because I'm taking the trace of the spatial part, and the trace of the spatial part is 3p. Okay, this is equal to 0, and h I define as a dot over a. So this tells me that rho dot is equal to minus 3h rho plus p. Okay, so this is the second equation that we have. Let me just write it here. So here I define h to be a dot over a, and then from energy momentum conservation, we get rho dot equals minus 3h rho plus p. So these two equations are sufficient, are basically all of the dynamical equations that we need to solve. These equations and their derivatives will all of the Einstein equations are reduced to these two equations, are derivable from these equations and their derivatives. So we don't need to actually derive any other equation. We can just take the derivatives of this. Okay, let me also give names to these equations. So this one is called the Friedman equation. And this one is, well, I don't know if there is a name for this equation. This is, maybe sometimes it's called continuity equation. So this is just energy momentum, energy conservation, essentially. Any questions so far? Okay, so what would be the goal? We said that we have some symmetries. The symmetry fixes the form of the metric up to this parameter a, or this function of time a, and they form they fix the form of the metric up to this function of time A, and they fix the form of the energy momentum tensor up to these two functions, rho and P. So the goal is to find the time dependence, or to find these functions, right? So imagine we have observers who live on this space-time. They want to see what, or we want to determine what is the history that these observers are experiencing. Why do we ask this question? For obvious reason. We think that we live on a space-time which is homogeneous and isotropic. We measure what kind of matter we have on this space-time. We want to understand what happened in the past. So solving these equations, solving for these functions of time, it helps us to determine the history of the universe, to understand what happened in the past. That's the phenomenological goal of this exercise that we are going through.
Sorry, can I ask something?
Yes.
Okay, in this metric, if we can consider the A as it gives us the evolution of the distances that what we measure at one time, and it can change when we expand it or something. What is the physical meaning that we can give of the H?
Oh, okay. That's exactly what I wanted to discuss now. Thanks for asking. Any other question? Okay, let's talk about the meaning of this H parameter that I define. So this H is called a Hubble parameter, and it's called and its interpretation is that it gives us the Hubble law. So there is a Hubble law on FRW cosmology. What is the Hubble law? It's the following concept. So let us again look at the metric. Now let me simplify this. So how do I simplify? Let's do the following. So we know that so we said there are three types of metrics, right? These three types of metric, I can also write them in the following form. Perhaps you have seen it in the exercises. So this R of chi is equal to chi if k is equal to 0, if it's equal to sine of chi, if k is equal to 1, and if it's equal to sine hyperbolic of chi, if k is equal to minus. So now let us consider some observers on this in this cosmology. So let's talk about those preferred observers. So I said there are a set of preferred observers who observe the universe to be homogeneous and isotropic. So let's talk about those. What is the force velocity of those observers? So I claim that the force velocity of those observers are given by just 1, 0, 0, 0. and they are geodesics. Why? Because well, this is basically how I defined it. I define this time variable as being the measuring the time of this observer. So that's how, therefore, if the proper time of this observer is measuring the t variable that we have, then therefore velocity has to be this, because the proper time is just t. Now the question is that are these geodesics? And the answer is also yes, these are geodesics. It's very easy to verify that they are geodesic, because they, if I look at the geodesic equation, d by deta of u mu equals 1/2 d mu g alpha beta u alpha u beta. Since only the 0th component, the t component of u is non-zero, and since the t component of the metric is a constant, then the right-hand side is 0. And also the left-hand side is 0, because the u, the 0th component of ut will also be a constant. So both the left and right-hand side are 0. So this equation is satisfied. So these are geodesic, and these observers are called co-moving observers. So these are co-moving observers because they sit at the fixed coordinate, at fixed set of coordinates. So that's why they are called co-moving. And they are geodesics. But they move along geodesics. Okay, so now let us consider two of them which are close to each other. So these two. So they are at some separation chi, and that separation remains the same with time because they are at fixed values of this the spatial coordinate. Now let us compute, if let's imagine this chi is very small, the distance between them is very small, and let us evaluate the physical distance between them. So consider two nearby co-moving observers, say at 0 and chi. Then the physical distance between them, so the physical distance, let me call it x physical, between those two is a function of time, and it is given by a. So look at this metric. We are considering two observers which are at a small distance chi with respect to each other. The physical distance between these two is given by a times chi. So now then, what is the velocity that they measure? So I'm one of them, and I measure the velocity of the other one. I just take the time derivative of the physical distance. So what I obtain is the velocity, the physical velocity is given by a dot over a times a chi, which is x physical, which is h times x physical. So the velocity that I measure for other co-moving observers, it is proportional to the distance to those co-moving observers. And this is called the Hubble Law. Of course, I was doing it only when they are infinitesimally close to each other. So eventually this computation becomes meaningless. But when they are close to each other, then they follow this Hubble Law, or this property, this relation between velocity and distance, which is called the Hubble Law. So this is called, this relation that velocity is proportional to distance is called Hubble Law, and h, which is a dot over a, is called the Hobel Pyramid. So this is a quantity which has dimension in our units, in natural units. When we set c to 1, this has dimension of 1 over length, right? Velocity is dimensionless. Therefore, h has a dimension of 1 over length, or 1 over time from here. However, now if we don't go to the natural units, then it has a dimension of velocity over distance. So for our universe, the natural units to measure this quantity is kilometers per second, because the astrophysical objects have typical velocities which are of order of tens of kilometers per second, and the distance, the typical distance for cosmology is megaparsec. So therefore, this is normally measured in kilometer per second divided by megaparsec. So in our universe, the current value of h, which is called h naught. So h naught means that the current value, of course, this is a function of time in general, is approximately 70 kilometer per second per megaparsec. Megaparsec is of order of the distance to the next galaxy, for instance. And the velocity of say Earth moving around the sun is of order of tens of kilometers per second. It's, I think, 30 kilometers per second. So these are the typical velocities and distances. Did I answer the question?
Yes, thank you.
Any other question so far?
Yeah, one question. Since we're considering all this in a large scale, up to what extent we are sure that this metric is okay, and not considering other metrics?
You mean in our universe?
Yes.
It's correct at larger scales. It's correct as far as we can see. But of course, if you go to a smaller scales, then it becomes inhomogeneous, and so as you go from very big scales, you come to smaller scales, you will see that there are fluctuations. in fact, even at biggest scales, I shouldn't have said that it is exact. Of course, there are fluctuations even at bigger scales, but they are extremely small. They are of order of 10 to the minus 5, the fluctuations of this metric. So, so we think of our universe as being basically we do perturbation theory. We think of it as being FRW plus perturbation on top of it, which means that it's not FRW, because FRW is this exact model. So in a sense, this is wrong, but this is at larger scale a very good approximation to what we see. And then as we come to a smaller scale, it becomes worse and worse. And when we have black holes in our universe, so it's not at all like this. Okay. So we had these equations, and the goal when we do a FRW cosmology, or in general when we do cosmology, the goal is to understand the history, to understand what happened before, and then try to predict what will happen in the future. Although usually that's not very relevant for human time scale, because the cosmological time scales are much longer, so it really doesn't matter what happens in future for us. But we are very interested in understanding what happened in the past. So we want to solve these equations. Of course, this cannot be solved like this, because I need some extra information. But here, as you see, there are 2 equations and 3 unknowns, A, rho, and P. So we need to know some relation between P and rho, or if we know a relation between P and rho, then we can solve these equations. And that relation between P and rho is called the equation of a state, what relates pressure to energy density. But depending on what kind of matter or what kind of substance we have, then this is a more perhaps microscopic question of how the pressure that substance is related to its energy density. So that has to be supplemented to this system. It's not Einstein equations, Einstein theory doesn't know anything about that. So we need the equation of a state. So maybe we can add a page here. And this is stuff I think we don't need anymore. Equation of a state. So it's convenient, and often it's a good description to have to consider a very simple equation of a state when P is just proportional to rho with the proportionality constant that is called W. So what are some examples? So one example is radiation. Gas of radiation, thermal photons. In that case, pressure is 1/3 of rho. So W is equal to W is equal to 1/3. Oh, let me say something before that, before going through examples. Let's just see what happens if P is equal to W rho, because now if this is the case, then we have rho dot is equal to -3h times 1 plus W times rho, which means that d by dt of log of rho is equal to -3 1 plus W d by dt of log of A, which means that rho is proportional to A to the -3 times 1 plus W. Okay, let us now consider examples. So example 1 is radiation. W equals 1/3. Then I will have rho radiation proportional to A to the -4. Other example is matter. It's called matter, by which I really mean non-relativistic matter. So for non-relativistic matter, pressure is negligible compared to energy density, because most of the energy density comes from the rest mass, while the pressure comes from kinetic energy. So this is non-relativistic matter. In this context, it's always called just matter, and W is approximately 0. In this case, we have rho matter proportional to A to the -3. So this should be intuitive. This scaling with A to the -3 should be intuitive, because what is the energy density of non-relativistic matter is just the mass, the rest mass of these matter particles per unit volume, right? Their energy comes from the rest mass, but the volume is expanding like a cube in this geometry, in a far W geometry, right? Because if you look here, if I calculate the volume of a box, it expands like a cube. So this is not surprising. The fact that rho goes as 1/a cube is just the fact that the volume dilutes, the number of matter particles remains the same. So therefore, energy density goes as 1/a cube. Why is it going as A to the -4 for radiation? Is because of something that we will talk more about. It's because of the redshift. So if you have photons, as the universe expands, we have two effects. One is that the photons dilute, so we will have less of them per unit volume, but also their wavelength stretches with distance. So the frequency goes down by another factor of A. Therefore, we get 1/a to the 4th. One other example is lambda, the cosmological constant. Sometimes it's got dark energy. So that corresponds to W -1. So what is cosmological constant? Cosmological constant is, if I consider T mu nu to be equal to minus lambda times G mu nu. So if I just add a constant to my action and derive the energy momentum tensor of the action, then that would be proportional to G mu nu, would have this form. And now of course, if you look at the definition of P and rho, you will see that rho will be equal to lambda and P will be equal to minus lambda. So rho is equal to minus P is equal to lambda, which means that W is equal to -1. And of course, this is constant. So it doesn't change with the scale factor. It's also sometimes it's useful to think of the curvature. So remember here we have also a contribution coming from the spatial curvature of these slices. Sometimes useful to think of that as also a contribution to as a source of energy density, so as a fictitious energy density, just to put everything together. So that would look like the curvature or space, the space curvature is equivalent to substance with W equals -1/3. Just from the behavior of this this term in here, because if I take W equals -1/3 and plug it in here, what I get is that the energy density goes as 1/a², which will be this behavior. So I just invent this this fictitious substance, which I call the space curvature, for which rho k is proportional to a minus 2. Okay, so now what does it mean? If you have a universe which is expanding with time, what expansion in time means that this scale factor is growing with time. Then these different components, well, of course, you could consider other components too. These are the most relevant ones when we discuss cosmology in our universe. These components will dilute in different ways with time. Or maybe they don't dilute. For instance, the cosmological constant doesn't dilute. While this radiation dilutes faster than anything else in this list. So what does it mean? If you have a universe which has a mixture of radiation, matter, cosmological constant, and curvature, as time passes, different components become important at different times. So as I go to very early times, when the scale factor is small, then the radiation becomes large. Then at some later times, matter becomes important. If there is curvature, then curvature becomes important. And finally, the cosmological constant becomes important. It's not always like what I said. The story could be more complicated. Sometimes something can be so important that it completely changes. For instance, we might stop expanding and then recollapsing. So that we never get to a stage in which cosmological constant dominates. But if you imagine that we have expansion in our universe, then that's the general trend. At the earlier times, the components with larger W are important. Or when the universe is smaller, the ones with larger W dominate. And then when the universe expands and becomes larger, the ones with the smaller W dominate. Any question? Okay, is there any constraint on the equation of the state? So there are some conditions on how the T mu nu of matter might behave. Now you could imagine, for instance, some version of positivity of energy to constrain the types of matter field or the types of energy momentum tensor that we can have in here. So one of them, which is perhaps the most important one, is called null energy condition. If you remember, I mentioned it before in the context of black hole area theory. So for instance, we saw that if null energy condition is satisfied, then the area of black hole horizon cannot decrease with time. And we related that to the second law of thermodynamics. Sorry, it's not null energy theory, it's null energy condition. Condition, or NEC, or NEC, which says that K mu, T mu nu has to be larger than equal to 0 for all null K mu. So now in particular, let's take this null K mu to be, so what would it look like? Say there is a null K mu that propagates in direction 1, right? Just by the fact that it's null, it has to have the following form. There has to be let's call this A, big A, the zeroth component. And then the first component has to be equal to A over A, little a. Now if I multiply this, so if I multiply this with the energy momentum tensor of a perfect fluid, what I will get is that I should have rho plus p larger than equal to 0. So null energy condition using this particular null vector gives me rho plus p larger than equal to 0. Which means that W should be larger than or equal minus 1. So this is a constraint that is often imposed on the components of the matter, that or the forms of energy, the equations of a state that are allowed in cosmology. Of course, people look for violations of this. It would be interesting to see violation of this empirically. But there is a theoretical prejudice that W has to be larger than or equal to minus 1. Any questions so far? Okay, so now given the equation of a state, we can solve this system. So for in part, or of course we don't have, we can have multiple components of matter with different different W's or different equation of the states. Then it becomes a bit harder to solve it. But in principle, if I say what components of the matter I have with what equation of the states, then I will be able to solve it. So let us just consider a simple example and solve it and see what we get. Okay, so let us consider matter dominated cosmology. So if you have matter dominated, so what is the problem that we want to consider? We want to say that W is equal to 0. So rho is equal to rho naught times A naught divided by A cube, where not 0, this index 0 means now. I just pick this arbitrary time, some arbitrary time, and refer to values of different quantities at that time as with index 0. So rho naught and A naught are just constant. Or what else? Let's imagine that K is equal to 0. So we have flat cosmology. Okay, and then we can solve the system. So we first of all, this equation, this has already solved the energy conservation equation. Oh, and let me also say that imagine the Hubble parameter, the Hubble expansion rate is h naught at the current time. So then the equations that the Friedmann equation is h squared equals 8 pi g third times rho. So in particular, rho naught is just related to h naught. So rho naught and h naught are not independent quantities. Rho naught is just 3 h naught squared over 8 pi g. So now what do we want to know? We want to know what is A of t, for instance. Or more importantly, what is A of h of t. But of course, if we know A of t, then we can determine h of t. So that's the goal. Now, of course, this is a simple differential equation that we can solve easily. So A dot over A, so h squared is A dot over A squared is equal to 8 pi g rho naught over 3 A naught over A cube, which is nothing but h naught squared times A naught over A cube. So this tells me that So one thing that I can do here is that I can do a rescaling of A and set A not to 1. So let me do it just for simplicity. So whenever you see A from now on is A over A naught. I just multiply A by a constant, which then can be reabsorbed into rescaling of the co-moving coordinates. And since here we are in flat cosmology, there is no spatial curvature, so there is no K to worry about. So we can freely rescale the co-moving coordinates, not worrying about K becoming different from 1 or minus 1. So I set A not to 1. So parentheses, A not equal to 1. Then I get A dot times A to the 1/2 is equal to H naught, which tells me that 2/3 A to the 3/2 is equal to H naught T. Or A is equal to 3/2 H naught T to the 2/3. So I have also fixed an integration constant for T. I set T equal to 0 to be the time at which the scale factor becomes 0. Right, so as you see, the scale factor, as I increase T, the scale factor grows as T to the 2/3. Now, as I decrease it, it decreases. At some point, it hits 0. So I fix the integration constant in this equation to be such that T equal to 0 correspond to the point when the scale factor hits 0. And then given A of T, then we can determine H of T, which is given by uh, 2/3T. So what do we see here? What we see here is that as a function of time, so this H of T decreases as a function of time, but it blows up at T equal to 0. So this T equal to 0, or let me say this, H of T going to 0 is infinite, and this is called, and this is a singularity. So if, for instance, we calculate the curvature, scalar curvature of the metric, that will be proportional to H squared, and that blows up as H goes to infinity, or as T goes to 0. So this singularity at T equal to 0 is called Big Bang singularity. Why is it called a Big Bang? Because you have this H, this Hubble scale, it determines the expansion rate. So what we see is that the expansion rate is the start singular is infinite at T equal to 0, and then with time it slows down. So the way to think about this is there is an initial explosion, and then with time it is this expansion slows down. Okay, so this is a simple FRW model. Starts from singularity and then it expands. Now, if we add additional components, then we will have different histories. But so this is one example in which, imagine if we today we measured the expansion, the Hubble parameter. So this is the type of question that we can ask in cosmology. If today I measure the Hubble parameter and I measure the energy density of the universe and I measure the curvature, the spatial curvature, then I can determine the history of the universe, assuming that this is the only matter content, and nothing dramatic happens at earlier times, or no phase transition happens at earlier times. We know that I would know that I started from a singularity, or my universe started from a singularity at a particular time. Oh, by the way, this is also important. Now we can also ask what is the time now, or how far in the past this Big Bang singularity happened, and we can answer it, right? Because we said that now we measure Hubble to be H0, so that determines T0. Or the age of the universe, the time it took. So T0 will be the time from the Big Bang until today. So since we know h of t and we know H0, we can determine T0, the age of the universe. So here T0 will be just 3. T0 will be just 2/3 H0. So if I measure H0 and measure curvature, I know that the age of the universe, the time from the Big Bang singularity until today, is just 2/3 H0 in this matter-dominated universe. Any question? Okay, so let me mention a few things about related to photons or null geodesics. So null geodesics or photons are very important in cosmology. They are always important in GR, but especially in cosmology, because that's how we observe the universe, right? So the signals from different things, they travel along null geodesics, more or less, until they arrive to us. So we want to understand how they move and how to understand, how to interpret what we see, right? So the idea is that we are sitting here and we are watching our universe. We are receiving signals that arrive from earlier times. So we want to understand, for instance, if we receive 2 photons with some angle between them, coming from some early times, we want to understand what this angle, what distance that angle corresponds to. right? Of course, if we look over there and there is a tree or there's a mountain, and then there are two photons from two sides of the mountain arriving to us with some angle, we use simple Euclidean geometry to relate this angle to a distance. Now, once we live on a curved space-time, then this relation becomes more complicated. So we want to understand what is that complicated relation. Of course, that relation is fully determined once we know the metric, because we are just solving the geodesic equation on this metric. So to talk about null geodesics, it's always useful to work in conformal coordinates, conformal flat coordinates. So let me remind you, conformal means in GR, when we say conformal transformation, what we mean is a transformation that preserves the angle. Conformally flat means that conformal flat metric means a metric which is related to the flat metric by a transformation that doesn't change the angle. In particular, if we write the metric in a conformally flat way, then the null geodesics will travel at 45 degrees. So that's the main usage of conformal coordinates. To be able to draw diagrams with photons traveling at 45 degrees. So that's the motivation to introduce conformal time. So again, the metric is looks like minus dt squared plus a squared. Let me again focus on the flat case, dx squared. But if it's not flat, then this part will be I take one of the three forms. In either case, the radial geodesics in terms of that chi coordinate would be the same. So everything that I said would hold there. In fact, let me just keep it general. So how do we write the general metric? Let me call it the sigma squared, and then the sigma squared is the chi squared plus r squared of chi, the omega squared. And r of chi again is equal to sine chi if k is equal to 1. If we are spherical, if is equal to chi if k is equal to 0, so we are flat, and it is equal to sine hyperbolic of chi if k is equal to minus. Okay, so what is conformal time? Conformal time is to write, we introduce this so that we can write this metric in a way that at least in the t chi part, the t chi or the t chi part of the metric look like the flat metric, Minkowski, 2D Minkowski metric. So I factor out the scale factor, and I will have dt squared over a of t squared. This is very easy to do in FRW cosmology. So I only need to define the conformal time tau as the integral of dt over a of t. So this quantity is called the conformal time. So now, how does the metric look like in terms of the conformal time? In terms of the conformal time, I will have a squared of, now of course t is a function, tau is a function of t, I can invert it, so t is a function of tau. So I will have a as a function of tau minus d tau squared plus d chi squared plus r squared of chi d omega squared. So if I look at radial geodesic, so say I pick the center to be where I live, and then radial direction would be along chi. So if I look at radial geodesics, then they null geodesics, radial null geodesics, they will move as if they are in Minkowski. If I want to plot them, I can just plot them in 45-degree lines. So that is, this conformal time tau is very useful for plotting diagrams, because now I can draw things like this. So this is the chi direction, and I can say I'm an observer. I'm an observer living at some time tau naught, and then I'm just watching what is happening in the past, and what I'm seeing is the everything along my past life. In particular, in this case of matter-dominated cosmology, what we saw was that at t equal to 0, there will be a singularity. So we can find the conformal time in that particular example, right? So if I take matter-dominated cosmology, then what is the relation between tau and t? Tau is integral of, so we saw that a is proportional to t to the 2/3. So we have the integral dt over t to the 2/3 with some proportionality constant. Let me just put it c here. So therefore tau is given by 3c t to the 1/3. So in particular, tau of 0 is equal to 0. Big Bang happens at tau equal to 0. So for matter-dominated cosmology, I will have the Big Bang singularity here at tau equal to 0. Any question? Okay, if there is no question, I think we are done for today. There is one thing that I should have said, I think, before. Which would be useful. So when I talked about different components of matter, so let me just mention it. We can also go over it again next time. But I mention it now because it's useful for doing your homework. So there is something called omega. So if you look at the Friedman equation again, imagine we have different components of matter. Then let's say at t naught, some arbitrary time, but in particular in cosmology, we mean today. I divide this equation by h naught squared. then what I get is that 8 pi g over 3 sum over I rho I divided by h naught squared minus k divided by a squared h naught squared is equal to 1. So we define omega, big omega I, to be 8 pi g rho I today. So let me put it 0 here. 0 here means, here 0 means today, divided by h naught squared. We define omega in this way. We also define omega k in an analogous way. So we say define as k divided by a squared. Of course, this becomes a naught squared, h naught squared. So with this definition, then what we'll have is the sum over I omega I plus omega k is equal to 1. So this is just a matter of definition. It's common to define to specify the matter content of the universe in terms of these omegas. So if I tell you what is h naught, h today, and what is omega of different components of the matter, I have specified. I have specified what the values, the ratios of different components. Like for instance, in this example here, I had k equal to 0, and all of everything, the only component was just matter. So in this example, I had omega matter equal to 1. So the important thing is that the sum of these omegas have to be 1. Now either all of it is in this part, in this rho I components, and then the curvature, the spatial curvature will be set to 0, so it will be flat. Or if this sum is not equal to 1, then there will be some spatial curvature. But in any case, the sum of all of these omegas is equal to 1. So for instance, if I tell you that I have a matter-dominated universe with omega matter equal to 1/2, but no other type of energy density, then you would know that there will be an omega k equal to 1/2. So the spatial curvature of that universe has to be negative, because this sum has to be equal to 1. Okay, that's it for today. If you have questions, then please ask.